Greetings everyone. Today we're going to explore graphing square root functions. Let's take a look at the parent function for the squared root. This is very important in order to graph future square root functions. So this is something that you want to try to commit to memory. To start off, I know that I can't take the square root of a negative number and have it be visible on a graph, as it would be imaginary. So let's start off with 0. The square root of 0 is 0. I can graph that point. Let's plug in 1. The square root of 1 gives me an answer of 1. So 1, 1 is my next point. If I was to plug in 2 next, the square root of 2 is a decimal. So I'm actually going to try to avoid that. Let's find a number that's a perfect squared. Let's jump over to 4. The square root of 4 gives me an answer of 2. So at 4, I'll be at 2. Let's jump to the next perfect square, 9. If I plug in 9, the square root of 9 is 3. So I can jump up to 3. And I know from there that the graph will continue. So as I graph that parent function, I need to make sure to draw an arrow going a little bit up and off to the right. Let's talk about our domain. Our domain value is the x values, meaning how far left to how far right. That deals with our x's. In our parent function, our x values are all greater than or equal to 0, meaning I can't have negative x values. Our range is dealing with the values of up and down, meaning your y values. In my parent function, all of my y values are greater than or equal to 0. I can make note of the domain and range in the table, but also on the graph. Let's talk about the transformations of that parent function. In this case, we're going to use the a, and we're going to call that the vertical stretch. The k value is going to be our vertical shift. Therefore, if I'm adding a number, my graph goes up. If I'm subtracting a number, my graph goes down. The h value under the radical is your horizontal shift. Now that horizontal shift, you'll notice it says minus h. So there's a special rule when we take a look at the signs for our horizontal shift. Let's take a look at how the y equals a squared root of x minus h plus k looks when we utilize these numbers to transform our graph. Let's start off with our parent function table. We had 0, 0, 1, 1, 4, 2, and 9, 3. Let's take a look at the first value, the 2. That is our vertical stretch. Vertical meaning it applies to our y values. So we're going to take our y values and times them all by 2. This creates a new table that keeps our x's, but now our y's have changed to 0, 2, 4, and 6. Let's take a look at our plus 4. Notice this plus 4 is a different sign than our transformations up above where it says minus h. So because that says minus, we actually do the opposite because it's opposite of the parent function. So we're going to subtract 4, and remember this is horizontal shift. So horizontal implies the x values. So we're going to subtract 4 from each x value. So for under the radical, you do the opposite of what it says. Our new table would read negative 4, 0, negative 3, 2, 0, 4, and 5, 6. We've got one more number to deal with, and that is our -3. Our -3 is our vertical shift. That means it affects our y values. It's outside of the radical, so we treat it just as we see it, and we are going to subtract 3 from each of our y values. That gives us our final table of -4, -3, -3, -1, 0, 1, and 5, 3. Let's take a look and graph those points and see if they make sense. -4, -3, -3, -1, 0, 1, and 5, 3. So that's our starting point. We didn't flip or anything like that, so it looks the same, but it's stretched out because of the vertical stretch, and it goes off to the right. So our domain is our x values. X values, look at my x values, they start at -4. All my x values are bigger or equal to -4. The range is dealing with your y values. The lowest y value I have is -3. All my y values are bigger than or equal to -3. One way to double check your understanding is to go to Desmos.com. When you're in Desmos, you have the keyboard in the bottom left. You have the square root button on that keyboard. Just make sure that you use the left and right arrow keys to get those numbers where you want them to be. So in this case, I can check my work and I can see that yes, my domain and range are correct. And if I zoom out, I can see that this graph does go on forever to the left, to the right and up. For our second example, let's approach it the same way with our table. We're going to start off with our same parent function table. We want to work left to right. The first thing I notice is this negative sign. That negative sign technically could have a -1 here. That'll help you remember that that is our vertical stretch, meaning I'm going to times every y value by -1. That gives us our second table. Our x's stay the same, and our y's are now 0, -1, -2, and -3. So we can already see that that was a flip that occurred. Let's take a look at our next value, +2. It's under the radical, so remember that this is our horizontal shift, but we want to do the opposite sign. So I'm going to take every x value and subtract 2. That creates our next table of -2, 0, -1, -1, 2, -2, and 7, -3. For our third move, we have a +4. That's our vertical shift. So I'm going to add 4 to my y values. That creates a new table and our final table. Our y values are now 4, 3, 2, 1. Let's graph and see what that looks like. -2, 4, -1, 3, 2, 2, and 7, 1. So you'll notice that this time it's curving down and to the right. So our vertical stretch of -1 flipped it vertically. Our domain is our x values, our range is our y values. Think of it alphabetically if that helps. dx, ry. Our x values, the smallest one is -2, the rest are bigger than -2. For our y values, our biggest is 4. The rest of my y values are below or less than or equal to 4. Again, we can use Desmos to check our solution. If I type in the negative square root of x plus 2 and plus 4, I can see that it is true that our vertical stretch flipped our graph. We can also again zoom out to see how that looks over time. Let's take a look at one more example for squared roots. Let's start off with our table of 0, 1, 4, 9, 0, 1, 2, 3. I would recommend memorizing that, or you can always recreate it by using that parent function. Let's start off with our first value. Our vertical stretch says 1/2. So I'm going to times all my vertical values, my y values, times 1/2. That creates our secondary table. We end up with 0, 0, 1, 1/2, 4, 1, 9, and 3/2. So we do have a fraction in there. Our second value says plus 3, our horizontal shift. We need to do the opposite. So we're going to subtract 3 from each x value. That creates our next table of -3, 0, -2, 1/2, 1, 1, and 6 and 3/2. Our final move is our vertical shift. We're going to subtract 2 from each y value. That creates my final table of -3, -2, -2, -1 and 1/2, 1, -1, and 6 and -1/2. Be careful with those fractions. Think if I have $1/2 and I lose $2. I'm down to -$1.50. Here I have 3/2, or you could think of this as 1.5. If I have $1.50 and I lose $2, I have -$0.50. You could also, of course, find common denominators to subtract fractions. Whatever's easiest for you. Let's graph these values. We end up at -3, -2, -2, -1.5. Be careful with those halves. 1, -1, and 6, -0.5. So notice those y values are scrunched together because my vertical my vertical stretch was less than 1. It was 1/2. That vertical stretch right here. So it sort of squished the graph. Our domain and range are x and our y's. Our smallest x value is -3. The rest of the x values are bigger than -3. Our smallest y value is -2. Look at the y-axis. All of our y values are greater or bigger than -2. Again, we can check our graph in Desmos, and I can see that yes, it is a squished squared root graph because of that 1/2 vertical stretch. I can also check a couple of extra values if I need to. For our next class, you'll want to have your foldables all filled out. This one was your squared root, but you also need to take care of the cubed root. It's the same process, we're just using a different parent function. Also a reminder that our next test over this half of the unit is going to be before Easter break. So whenever our last class of the week is, so for most of you it's going to be Thursday, but double check your calendars. It's before the long weekend. Take a look at the next video and let me know if you have any questions.